Good afternoon, all. Thanks for joining us today to continue following the 6G Research Visions webinar series. Today, we address the 6G localization and sensing by addressing enabling technologies, new applications, as well as future directions concerning research and development. Today, my name is Carlos Lima. I'll be moderating this session, and I'll be accompanied by the following experts that co-authored our 6G white paper on localization and sensing. Our first presentation will be given by Barend Van Liempd from IMEC that will give the details about the Terahertz spectra adoption for the next generation of wireless communications. Next, we have our colleague Hadi Sarienden from KAUST University that will talk about intelligent reflective surfaces. Our third presentation will be given by Yang Miao from Twente University that will talk about the beam space utilization for localization and sensing systems. Our fourth presentation will be given by Jaakko Suttala from University of Oulu that will discuss the role of machine learning and artificial intelligence in the next generation of wireless communication systems. Our fifth presentation will be given by Henk Wijsmers and Tom Svensson from Chalmers University that will talk about the joint aspects of sensing and communication in the 6G systems. Finally, we have André Barreto that will talk about the active radar sensing and the joint aspects with the communication systems. Before we start the actual presentation, I just would like to give you a few remarks regarding our webinar. First, we recommend you to use full name when you register your Zoom profile. We also recommend you to try to write short questions to the Q&A window at any given time, and try to do that either using your full name or anonymously. The dedicated Q&A questions and answers will take place by the end of the presentations. And we will record the webinar, including all the Q&A session, and the video will be made available afterwards in the event webpage. Also, we would like to say that in order to keep the discussion going, try to use the following hashtags: 6G, 6G white paper, 6G vision, 6G research, and sustainable 6G when referring to our 6G white papers and webinars. Okay, now I think we can go to the first presentation.
All right, let me know if this is fine.
Yes, we can see.
All right. So good afternoon, everyone, and thanks for logging into the webinar. So today I'll go and talk a bit about some of the technology challenges and some of the system level opportunities that we will have with 6G through the adoption of more spectrum in the, towards the terahertz domain. This talk is on behalf of our advanced RF team, and my colleague Joris van Driessen is actually the best contact if you have any follow-up questions, but of course also feel free to direct them to me. So towards 6G, there's the trend of growing data consumption, and it's expected to continue. So therefore, a logical step up from the current 5G allocation of spectrum is to consider even higher frequencies for operation, allowing higher bandwidth, and thus an easy way to increase the throughput. So as an example, we see regulatory bodies already preparing for this. For example, the FCC opened up spectrum above 95 gigahertz for development of new services and applications, as well as the WRC-19 expanding the mobile spectrum for an aggregated bandwidth of almost 140 gigahertz from 275 gigahertz onwards. Also, radar systems have traditionally operated at very high frequencies already, to make use of the larger bandwidth, which has the purpose of achieving high resolution sensing capabilities, way before there was a need or capability for such bandwidths in consumer wireless communication systems. In the automotive space, we already had a tradition of 24 gigahertz as an initial band, which is now quickly being overtaken by systems operating at 77, 79 gigahertz system. While there is also an outlook towards smaller systems in D-band with even higher resolution. So D-band being in the, say, 140 gigahertz range. For 6G, there's a number of applications and services that are expected to be enabled by this new spectral capacity, ranging from wireless point-to-point data connections to wireless backhauling for network backend connections. And the specs for such links also differ drastically from, say, 50 gigabyte per second to over 500 gigabits per second, and from short-range links of peer-to-peer connectivity to over 100 meters of link range. So it's truly a challenging application space, and we actually will still need to develop many new technologies before we can enable all or some of these cases. And there's more. So as I already mentioned, radar traditionally being driven by automotive for navigation and ADAS purpose. However, across all smart domains, such as health, mobility, cities and industries, we identify a number of novel types of applications have not yet been pushed into mass markets, while we do see industrial activity around all of them. For example, startups building new radars and new applications on top of these. Radar sensing is a feature of communication networks for small cells with many sensing nodes, can offer intriguing opportunities that today simply are not available. And if the same hardware could be reused to enable both communication and sensing capabilities, that's like the holy grail that I think differentiates 6G from anything else out there today. Here we actually show one of IMEC's reference radar designs for a D-band radar chip at 140 gigahertz, designed in CMOS using on-chip antennas. It shows that it's possible to reach large bandwidth and therefore very high resolution sensing, even in a very tiny package. This chip can sense using up to a 10 gigahertz bandwidth, resulting in about 1.5 centimeter of range resolution, which is about the thickness of your fingers. And it includes the full analog transceiver using an external phase lock loop or PLL chip to generate so-called chirp, which we use to detect people, their gestures and vital signs. However, the on-chip antenna comes at the price of silicon area, and no circuits can be placed underneath the antenna area. Finally, the efficiency is still limited by the FT and Fmax of CMOS, which today is constrained, relatively speaking. Which brings me to the next slide, where we basically think and want to show that in the future, we should come to a vision where the technology platform can enable and migrate from a pure play CMOS to a more of a 3D stack, where we allow the reuse of the area underneath the antennas, while also migrating the high frequency RF to specialty technologies such as a 3.5 compound, as well as tight integration with a third CMOS layer, enabling integration of dense logic and memory functions. This can lead to systems with smaller form factors, low loss RF interconnects, and high efficiency scalable systems. At the same time, having CMOS close to a 3.5 device, for example, a HEMT or a HBT, can allow for many new complex circuit opportunities and better performance. In fact, when looking for technology options, in terms of efficiency, actually indium phosphide is a very promising candidate to reach, for example, at 140 gigahertz. We see a much higher output power and efficiency for such indium phosphide technology compared to CMOS. Hence, even beyond just FT and Fmax, it can be shown that for practical designs, we can reach higher performance than CMOS, which ultimately will be critical for the rollout of large networks of likely smaller cell sizes. Showing this comparative nature of various technologies closer to the application level, Here we analyze the estimated power consumption for a transmit front end. We compare on the left a 16 array antenna array, and on the right a 64 antenna array. The latter needs lower output power per element to reach the same overall range. Hence, for the same range or link budget, both arrays can reach the same EIRP. And at the cost of size, the larger array can achieve vastly better energy efficiency for lower output power per element, whereas indium phosphide also vastly improves over silicon germanium and CMOS. So while CMOS could enable some short-range links, it has a trade-off and a cost in terms of energy efficiency. So for such transceivers on a block diagram level, it's important to also analyze the interconnect between the multiple chip technologies and clearly between the final RF, say a 3.5 tech and the antenna. So the multitude of technologies can come together using a multitude of packaging options, from simple to more complex one. We could list interposer, wafer-to-wafer bonding, or die-to-wafer bonding. And it's clear that the traditional IC design first approach will not remain feasible. These designs need to be carefully co-optimized to achieve the overall performance. At IMEC, we look at upscaling 3.5 to a silicon platform and to enable a high maturity and also a higher complexity that would allow our designer to have much better and much more improved designs. And there are several ways of doing that. So one of the ways shown here is what we call wafer reconstitution or a collective die-to-wafer bonding. So you start from a pristine indium phosphide substrate with the grown layers that will be needed to enable the devices that you need. Then these are diced and sorted, and they can be attached and planarized to large 300mm wafers, which can thus be processed and continue to be processed in the 300mm line using CMOS-compatible patterning schemes, which also allow us to even scale those devices down and to allow to make multi-level metallization schemes on top of these devices. And finally, there's also a second approach, putting the 3.5 directly onto the silicon by a selective 3.5 growth. This is what we call our nano-rich engineering process. In this case, we first grow the 3.5 in a high aspect ratio to trap most defects in the trench. And then a pillar is grown using overgrowth, in which the 3.5 active device can be engineered. So that's the top side of this pillar, shown in this SEM picture here, which in fact is gallium arsenide nano-ridges grown on top of silicon, which is standard silicon in 300mm. You can also see that we're very much inspired by the IMEC tower in Leuven when we developed this process. So now the nano-ridges on their own is not enough. Of course, we need to make complex structures to be able to make the devices, bipolar devices, M devices that you would need to build such nice power amplifiers as what the technology in fact promises to enable. And that's ongoing work. With that, I'd like to thank you for your attention and hope you are as inspired as we are towards enabling these exciting new technologies for the next era of wireless function in a 6G paradigm. Thank you.
Okay, thanks, Barend, for sharing your vision on and to providing us with new insights on how to use the Terahertz spectrum for the 6G communications. Next, we have Hadi presenting, talking about the intelligent reflective surfaces.
Thank you, Carlos. So next, I will be presenting the prospects and challenges of using intelligent surfaces at the intersection of communications, localization, and sensing towards 6G. So in 5G, the main two enablers were at the infrastructure level, the introduction of massive MIMO or increased number of antennas at base stations, and at the spectrum level was the introduction of millimeter wave carriers. Moving towards 6G, massive MIMO will continue to grow. Actually, we call it here ultra massive MIMO. It's basically just realizing what massive MIMO promised to realize. But in addition to that, at the infrastructure level, the reflecting surfaces, passive ones, are also anticipated to be introduced. And from the spectrum level, millimeter wave will naturally progress towards terahertz, as Barend just discussed. So such surfaces can significantly change the way we perceive the communication environment. So they would allow the network infrastructure to adapt to change in the environment, thus transforming what was naturally known as a passive wireless environment into an active one. Now, to be able to do that, the parameters of the IRS should be able to be tuned in runtime, this will allow eventually an extension in coverage, improved throughput, security, and positioning. And as well, the promising technologies appear to be of low power consumption and cost effective. Hence, they should be easily implemented on building facades and walls and ceilings as well. Now, the research on reflecting surfaces has been significantly booming over the past 2 years, and actually there are hundreds of publications already. It's hard to keep track of them. But we can do some categorizations depending on their type and their modes of operation. For example, we can distinguish between reflect arrays, which are the basic implementation of surfaces constituting discrete plane and matrix of reflector elements, and meta surfaces, which are provide much more functionalities, basically made of artificial metamaterials, and with enabling technologies such as CMOS and MEMS switches. And we could also distinguish surfaces between active surfaces and passive surfaces. Now, active surfaces are just basic extensions to massive MIMO, like ultra-massive MIMO systems, whereas passive reflecting surfaces just like redirect the beam with some phase shifts, and they allow low-cost circuitry. We can also distinguish surfaces, whether they are contiguous or discrete. Discrete are, of course, the first phase of operation, but as technology matures, contiguous systems, continuous surfaces might provide much more functionalities. We could also differentiate surfaces based on their modes of operation, so they could just simply be extra infrastructure to assist in channel estimation, or they could also change the modulation of the signals, phase shifting, steering, absorption, beam collimination, and polarization modification. Now, as the technology on surfaces is progressing, the prospects of localization using these surfaces is an important topic to address. So actually, the first implementations of surfaces were in the satellite and radar systems, so inherently they have some aspects of localization and sensing. A variation of techniques, the popular ones of time of arrival, phase of arrival, angle of departure and arrival, they can be adapted, they should be adapted to account into the presence of surfaces. But most importantly, the received signal strength, which could also be used for localization purposes, it can be significantly enhanced in the presence of surfaces, which can increase the added power gain. But there remain a lot of challenges. For example, the modeling of the surfaces themselves and the channel modeling is still not very well understood. Like, what are the hardware impairments of the surface? What are the mutual coupling effects? Also, the channel, how it looks like in the presence of such surfaces. The near field propagation should also be studied. It proposes challenges and as well as benefits. Basically, we drop the planar wave assumption, and by taking into account the curvature of the spherical wave propagation, we can have extra degrees of freedom for localization purposes. Channel estimation is another challenge to discuss. Basically, solutions might include like hybrid surfaces where some elements are still active to transmit pilots to assist channel estimation. The system architecture and the signaling is another paradigm where we have to look into either uplink, downlink, or sidelink localization in the presence of surfaces, how to control the IRS, how to design waveforms in the presence of surfaces that achieve the best of communication and sensing, as well as the implementation of simultaneous localization and mapping with the presence of surfaces, because SLAM techniques usually do not take the information of association of users with infrastructure, and IRSs are a priori known and positioned, so some research has to be done in this area. Note that these are the prospects of enhancing localization using surfaces, but the operation of surfaces themselves might require good localization techniques, especially if they are small in size and need to be located for operation. Some bonds are already being derived on the orientation and position errors using surfaces, both in the near and far field, and there have been some proposals of phase profiles for the surfaces that allow joint communication and sensing. Notably here from the results that the position error bound and the orientation error bound of a user equipment that's being localized is enhanced on the proximity of both surfaces and the base stations. Of course, it also depends on the exact position of the user. There have been also other studies that there are response for millimeter wave systems, and it has been shown that almost only 40 elements are sufficient to achieve enhanced localization performance. And basically, the system, with the presence of a surface, translates from a system of line of sight plus non-line of sight assisted to a two line of sight aided positioning system. There is also the prospect of localization using large intelligent surfaces, and these are the active surfaces. As opposed, and there are some studies that have discussed whether to go for distributed or centralized implementation of such surfaces, with the argument that with distributed systems, we achieve effective higher surface area, better robustness, improved positioning, but at the expense of increased complexity and extra hardware maybe to calibrate phase and cooperate between subunits. There is also the prospect of using spherical surfaces, and spherical surfaces can not only just like reflect the beam, but can also relay it from the other sides. They also promise to achieve better received signal strength and lower error bounds on localization. Note that with spherical surfaces, regardless of the position around a spherical surface, the information theoretic properties of localization are valid. Now, following also on Barend's introduction to Terahertz communication, and it's effectively rising and emerging, Terahertz brings a lot of possible application at the intersection of communication, sensing, imaging, and localization. They are superior to millimeter wave in the sense that they can support higher data rates at smaller footprints, and they're also different from optical communication in the sense that they interact differently with the environment, and they can still make use of the microwave characteristics as well, not just like laser-like communication system. Now, Terahertz system bring a lot of opportunities in for both localization and sensing, especially in sensing because the molecules interact in a specific fingerprints with molecules and has the possibility of gas and material sensing. And the typical technology for that is time domain spectroscopy, whether transmission or reflection based. But we argue that frequency domain spectroscopy can even provide better flexibility, and these are a few results here. So instead of just sending a pulse and time domain and sensing the environment by sending select frequencies and tuning these frequencies to be the resonant frequency of specific gases, we can detect more efficiently the oxygen or water vapor, for example. But not here, two problems. For example, the first one is how to select the frequency, and other one, how to avoid the high losses and hence the requirement of high SNR. I will touch on that in the next slide. There's also the possibility of high resolution of positioning, and this is also a proof of concept simulation using multidimensional scaling, just as to assist Terahertz localization. You can check more on our work in paper reference 1 here. So these two challenges can be facilitated for sensing, can be facilitated with the use of large surfaces, active surfaces at Terahertz systems, and mainly because there is a high degree of reconfigurability. Hence, we can choose which antenna element to operate at what frequency, and which one to operate and which one not to operate. Hence, we can assign what carriers to utilize. Also, how much can you put within a subarray affects the beamforming gain, and hence we can combat these losses, path losses, and hence have a higher signal-to-noise ratio. So both active and passive surfaces are important for Terahertz localization, communication, and sensing. The active one might appear as access points or signal repeaters, especially because they are as well can be realized in small footprints. However, the passive ones might be even more interesting, especially that like coherent large arrays at Terahertz are not mature. Even relay technology is not mature. Hence, given the latest advances in metamaterials at Terahertz, this might be realized even before conventional massive MIMO solutions. Note also that when we allow the antenna elements to be very close to each other, such dense utilization of antennas, separation less than the wavelength, we can approximate what is called as continuous metasurface. And this gives us an opportunity to utilize holographic communications. And hence, as opposed to the discrete case where using discrete antennas can only allow us to realize beams in specific directions, using a holographic radio allows us a much higher resolution in spatiotemporal resolutions. It also allows better security and accurate positioning. And this is also more readily realizable at Terahertz because densely packing sub-wavelength unit cells is enabled, especially in the emerging plasmonic solutions. Now, there are also still some challenges. We have to understand the noise and the propagation and blockages of Terahertz systems, the changes to the environment, the misalignment effects as well. Most importantly, when using large arrays, the propagation of the signal appears differently from one reflecting element to the other or from one antenna to the other. And this results in accounting for both spherical wave propagation as well as beam squint effects. Also, Terahertz components are energy constraints, and hence we might use some energy harvesting solutions to enhance the systems. I will try to finish with some research directions. It will be interesting to study how the heterogeneous implementation of millimeter wave / terahertz optical system could happen, how to do cooperative localization and tracking in a dense environments, IoT systems, and how to accumulate sensory information from multiple sensor and sensor fusion, how to combine surfaces with self-free massive MIMO, how to use machine learning techniques for fingerprint localization. We could also look into novel applications, for example, seeing through walls. If a surface is on the wall, why not see also through the wall, not only reflect a signal? Also biomedical applications, for example, if you have a surface as a patch on a t-shirt, it can reflect like vital information, biomedical information. It can as well reflect them just by taking advantage of the backscattered signal to report sense data to a base station. Cloud computing, security, privacy issues are also important. Maybe reflecting surface can enhance physical layer security, but as well, maybe we can do some coding at the surface itself. Eventually, signal processing should be modified to account for the convergence of communication and sensing at the Terahertz band using reflection surfaces, and hence maybe sensing and the localization can be piggybacked over the infrastructure or the resources of communication systems. So this is it for my presentation on surfaces. For more on the research that we do in our group, I recommend that you visit the communication theory lab of Professor Mohammed Sima Alwini, as well as the website of the information system lab of Professor Tariq Al-Nafouri.
Okay.
Thank you.
Thanks, Hadi, for the detailed discussion on how to use intelligent reflective surfaces with localization and sense systems. Next, we have Yang Miao addressing advanced antenna arrays.
Great. So good afternoon. My name is Yan, and my family name is Miao. I'm an assistant professor from Radio System Group, the Faculty of Electrical Engineering, University of Twente. So for those people who don't know about U20 yet, so it belongs to the 40U Federation of the Netherlands, together with TU Delft, Eindhoven, Wageningen University of Research. And our group radio system is just reformed this year to develop the research line of joint communication and sensing with joint expertise of antennas, radio propagation, and signal processing for beyond 5G system. So I'm here today to discuss one of the enablers for 6G localization and sensing and the interpretations and the visions towards the realization of this enabler in this white paper. And note that this slide is mainly focused on the overview of the concepts, the challenges and opportunities without technical details. And also we invite everyone to collaborate and push forward the concept to reality. So in this presentation, we cover the overview of 4 aspects. First, what is beam space and why is it useful? What are the unique traits of the beam space radio signals as well as channels? Second, we describe how to exploit the beam space for communication and sensing. What are the opportunities? And then we move on how to process beam space and estimating parameters and also get the information that we want. And in the last we overview what would be the research and implementation challenges. So what is beam space? Let's start with millimeter wave or microwave massive MIMO. Note that here we call it micrometer wave, but it is also referred to terahertz or sub-millimeter wave bands. As has been mentioned, we go to higher frequencies due to the previous precious radio spectrum resources, where the large bandwidth can be allocated in millimeter wave and sub-millimeter bands to boost the radio communication capability. But when the frequency goes higher, the physical size of the radiating elements goes smaller to keep the radiating efficiency. And with smaller sized radiating elements and a fixed array aperture size, each element can transmit or receive less energy, but a larger number of elements can be deployed in the same aperture size. On the other hand, to increase link budgets, we can either increase the transmitter power or antenna gain. The increase of the antenna gain can be either achieved by improving the antenna design or simply increase the number of antennas. In short, massive MIMO is actually one of the responsive choices when go to higher frequencies. The millimeter wave or the micrometer wave massive MIMO is a multi-user solution empowered by spatial multiplexing and beamforming. The spatial multiplexing is simultaneously transmit multiple independent streams where each could experience independent and unique propagation channel, hence to increase the spectral efficiency. And beamforming is essentially the transmission of coherent signals to form a coherent field towards certain direction. And the enhanced beamforming capability in 2D or 2.5D, which means there's a little bit coverage in the elevation domain, or 3D on the full field coverage space. So the beamforming capacity that is from 2D to 3D space is advantageous to overcome the haphazard loss in millimeter wave or micrometer wave bands, and also to mitigate the interference from different directions. And the beam steering or beam switching can guarantee the coverage of the beamformed system. So what is beam space? Before reaching that point, let's first have a look at the beam types. It is quite common that people refer to the millimeter wave beam as pencil-like, indicating that the beam width is narrow. When we're going to higher to terahertz bands, we expect even narrower beam, or we can call it a ray-like beam. As was mentioned in last slide, the beamforming is essentially a manipulating of field distributions, either the field amplitude or the phase. And according to this tutorial paper shown on the right corner, there were 4 types of beams. The first, as you can see in the figure, the first column is the simplest case, where the distribution of the field is uniform. It's basically a plane wave in the direction that is in transverse with the aperture opening. This behavior of propagation beam can be understood by using the Huygens principle, where all the infinitesimal secondary sources from the field is approximately planar and parallel to the previous wavebands. With this uniform phase distribution is useful for applications where the radiated beam is intended to travel in one specific direction, such as point-to-point communication or a radio telescope. And as the change in the waveband shape is very minimal, this type of beam is capable of transmitting energy over a relatively longer distance with little angular divergence, as described by the Gaussian beam approximation. The second column shows a beam deflection, or we call it beam steering normally, and where the direction of the outgoing beam is dictated by a slope of an applied phase ramp to project energy towards the observer in an oblique angle. A linear phase ramp at the aperture is thus required to negate the negative phase accumulation on the far side. And if the slope of the phase ramp is dynamic adjustable, either beam scanning or switched beam functionality can be achieved. For beam scanning, the directionality of the beam can be continuously switched through a given range of angles. And for beam switching, there are finitely many outgoing beam directions to choose from. This is highly useful to distinguish between different directions in the far fields, and is extensively used for applications such as radar, automatic alignment of point-to-point communication links. The third and fourth column here is for the near field case, where the different phase distributions can be achieved. So this, so the direct all fields for these near field cases, they direct all the fields towards the optical axis. For example, in column 3, the phase distribution makes use of the deflection angle of 20 degrees towards the optical axis, and the resulting field's profile in the vertical plane to aperture is shown here. And also for this, in column 4, it is a radially symmetric, linearly ramped phase distribution to produce the converge of an outgoing beam along the optical axis. So those are the near field and far field beam types. We all know that the role of beamforming in millimeter wave and terahertz massive MIMO and the types of the beams. But now let's have a look of an overview of how to generate the desired beam and what is the current state of art and challenges. So the beamformer can be grouped into 4 types. The first 3 is nothing new. For example, an analog beamformer uses a single column RF source splits among radiating elements. And it can only allow for a direction at one direction at a time. For larger bandwidths, that is at millimeter wave or sub-millimeter wave bands, the larger bandwidth is predicted to be 2 or 5 gigahertz. The beam squint is a well-known problem for analog beamforming architecture using phase offsets. The second type is digital beamforming, which allocates the dedicated RF signal and path for each radiating element. So with dedicated control of phase and amplitudes for each radiating element, it yields a higher flexibility regarding the transmission and reception. So it allows multiple or all possible directions at one shot, and also it enables the optimization of the phases according to the frequency over a large band. So the frequency squint could be mitigated by using digital beamforming, but it easily suffers from high hardware complexity and power consumption signal overheading. So the hybrid beamformer is to combine the advantage of the two, and it is nothing new, but there do have some novel network architectures. For example, shown in this figure, that is using selective networks and lens antenna arrays to reduce the required digital RF pathway, and also use analog Fourier transform to convert the signal space to the beam space. In addition to above just mentioned electrical beamformer approach, there were also investigations focusing on using the electro-optic effect to design the beamformer, which exploits the change in the optical properties of a material in response to the electric field that varies slowly compared to the frequency of light. Optical control of phases and amplitudes of the array elements presents significant broader bandwidth and smaller sizes compared to the electrical counterpart of the above mentioned three methods. However, there is also a cost that is leading to the elevated noise level that reduces the dynamic range of the system. So those noise level in optical domain could be coming from the spontaneous emission or the optical amplifier, or even the photodiodes that is caused by the Brownian motions. So while challenges and opportunities are always hand in hand, the opportunity is that the beamforming and spatial multiplexing empowered by sophisticated beamformer, the additional degree of freedom can be leveraged to perform multi-beam MAMO. And the challenges, in addition to the noise issue of optical fed beamformer, are also many in the design and implementation of beamformer in view of system performance. First, there were distinct requirements of beamformer for base stations and that for the user ends. For instance, a user end beamformer has power constraints due to battery and also stricter thermal requirements. Second, there are gaps between antenna design and beamformer design. For sub-6 GHz, the antenna design and beamformer design are okay to be isolated. And beamformer people simply assume 50 ohm impedance matching for antennas. And by simply putting antennas and beamformer together with brute force, the loss is still tolerable. But when the frequency goes to above 100 GHz, the separated design raises issues of high loss, and collaborations between antennas and beamformer is necessary. And on the other hand, integrated antenna on chip or antenna in package seems to have solved the problem. There were commercial beamformers available for 5G band like 28 or 40 gigahertz from companies like NXP, IBM, Qualcomm, Samsung, etc. But those millimeter wave beamformers are all situated with very simple patch antennas, and the sophisticated vertical or azimuth 3D antenna configurations are not employable to those beamformers. The active antenna array integrated with multi-layer circuit, which does not compromise the antenna array contribution, is challenging, but hopefully possible to achieve in the future. And moreover, the beam steerable spatial range is also very limited. For example, beam scanning in 2.5D or 3D spatial domain is rare but high cost. So besides, even though the fabrication for millimeter wave is still not a problem but fabrication at terahertz would also be challenging at this moment. So according to NTT's annual report this year, they just mentioned above 100 gigahertz millimeter wave and terahertz wave frequency bands are still immature fields for a production point of view. Again, the hardware part is challenging, but the future is promising. So after introducing wide Boulder beamforming and beam types and the beam generator,
sorry, it's just like we reached the 10 minutes, just to let you know.
Yeah, sure. Sorry, I forgot the time constraints. But here, so we finally introduced the beam space. So the beam space, the beam space indicates orthogonal beam modes. And when the beam width is very narrow with very focused, highly directive, high gain pattern, there is an increaseness in the spatial signal space. We can see that one beam with certain directivity is orthogonal to another beam focusing in another direction. And the orthogonal beam concept is very similar to the orthogonal mode concepts. And we can interpret the orthogonality of relay beam space as orthogonal modes. And this concept was first brought up from MIMO communication in recent decades, and now it can be moved on to for sensing purpose. I will skip all those aspects. Anyway, the beam space channel is convertible to the conventional radio channel by conducting data multiplexing. So when we have multi-beam or single beam, when we measure the beam space channel, we can do multiplexing those data, and then we can get an overview of the antenna and the environment interaction at those higher bands. And also going to higher bands, the characteristics of the beam space channel will be frequency dependent, highly sparsity. So obstructed line set will be highly unlikely, but the line set and null sites will be the trend. And we have to deal with the abstract blockage that could be caused by the moving human or moving vehicles, and we need to take predictive countermeasure against it. So the convergence of communication and sensing is kind of the main topic in this white paper. And for communication, the challenges are the countermeasure against dynamic blockage. As a solution, the sensing capability enabling the environment mapping, target identification, mobility behavior prediction, predictive beam source management are desired. And sensing algorithms shall be efficient, combined with online-offline process, whose runtime shall be within the order of milliseconds. As sensing capability is required to be embedded not only for base station, but also for user terminal as personal radar, either for outdoor or indoor use. There were other concerns like privacy. Sensor fusion with cameras for outdoor urban use is still acceptable, but for privacy-sensitive home use, EM-based solution for sensing without requirements of flattening and cameras and being contactless are the trends. So for research and implementation challenges, in short, are the following aspects. The beamformer implementation, the near-field beam space processing, and also what Heidi just mentioned, atmospheric attenuations and also multi-targets aligned along the single beam, how to sense in that scenario, and also efficient and explainable use of AI offline online processing to achieve the joint sensing and communication capability, and the hybrid use of sensor fusion with environment awareness context. I'm sorry for the overtime, and that is all for my presentation.
Okay, thanks, Yang, for showing how to take advantage of beam space signal processing for localization and sensing on the terahertz spectrum. Now we have Jaakko addressing the machine learning aspects.
Okay, thank you, Carlos. My name is Jaakko Suutala. I'm an assistant professor in artificial intelligence in biomimetics and intelligent system group at University of Oulu. And today I'm going to give you a brief overview of artificial intelligence and machine learning methods applied to localization and sensing of radio signals, the current status, and some vision of the next generation 6G system. Here's the outline of a talk, a little bit motivation and background, then some examples from localization and sensing domains, and finally some challenges and open issues. So our vision is that 6G and beyond system will be more data-driven. So it will be a combination of communication, sensing, and localization. And we could have a lot of sensors and a lot of high-dimensional rich sets of data sources. Can have a large number of observations, and also this observation can be very high dimensionality. And also this system will be complex with this noisy, non-linear, non-stationary, and even multimodal data. So this kind of data-driven approaches can there help supporting more traditional mathematical models and low-level signal processing. First, by optimizing very large set of parameters jointly, and then we can also produce this kind of low-dimensional representation of high-dimensional data for further processing. So with the machine learning, we can enable high-level reasoning, adaptivity, predictivity, and even the proactivity of the system. And also, AI and machine learning will be used to help the integrating kind of the subcomponent of 6G system. For example, different techniques of intelligent reflective surface beamforming, passive and active sensing, for example, using radar. So it can be some kind of integrated or glued kind of methodologies we can apply it in the each of these components itself, and then combine to different kind of sources together. And furthermore, we can kind of extract higher level information. For example, here using this kind of programmable meta surface, we can actually image and recognize different human behavior from those images. So we can end up kind of end-to-end learning of high number of parameters, combining multi-source of data for prediction and decision making. Here's an overview of landscape, different machine learning concepts in location and sensing domains. So we can use supervised learning for mapping, predicting location, recognizing objects. Unsupervised learning, discovering patterns, low dimensional representation of data, and up to the reinforcement learning for example, to do cooperative locationing, autonomous navigation, and optimal controlling of these subsystems. Here's some example of current machine learning tool, kind of biased view, but this could be a kind of helpful starting point for the next generation system as well. So the deep neural networks is one of the hottest topics in many application areas nowadays. These methods are good feature extractors from structured data in image processing, speech and audio processing, things like that, and also has been applied recent years a lot in this wireless communication area. Those have some disadvantages, needs a lot of labeled data to train the parameters. They are also black box kind of models, so no proper uncertainty quantification of their prediction. So these models usually don't know when don't know what they are predicting. So for example, we can use Gaussian processes, one family of algorithms from norm-parametric Bayesian domain. They can handle prior knowledge, high-dimensional data, but can have some challenges to scale the huge data sets without some sparse approximation methods which are already available today. But they naturally gives us uncertainty estimation of the prediction, which could be very important in many safe critical applications where we want to know when the model is predicting wrongly And also these models can go deep. We can build hierarchical architecture using this kind of approach, which is really hot topic currently in machine learning. And then we can have this kind of sequential Bayesian state space models, which are useful in localization in general. So modeling temporal and dynamic system. We can build motion models for moving targets and also combine data from heterogeneous sensors probabilistic manner. So 6G requirements of accurate position and the new services will set a new challenging goals to AI and machine learning research, where this kind of approaches can be a starting point, and we need to combine and develop these approaches further. Shortly about the machine learning for localization, typically used in complex environments like indoors and urban canyons where the GPS signals cannot be detected. We can use supervised learning to build this kind of using the fingerprint data, for example, from this channel state information to map the high dimensional CSI features to location information, discrete or continuous, using a classification and regression model, for example, deep learning, Gaussian processes, ensemble learning, so on. And we can combine this to hybrid models where we combine these fingerprint models with more physics-based signal propagation models to do trilateration and triangulation combined with this fingerprinting. As well as we can use post-processing using the Bayesian filtering and smoothing to add target motion priors and things like that. And in unsupervised domain, we can extract hidden patterns from the data, divide the feature space in different high-level clusters for further processing, or we can use dimensionality reduction methods such as principal component analysis, autoencoders, and so on. And one example of this presented in our white paper is a channel charting, where we use this dimensionality reduction method for this high dimensional CSA data to extract this kind of low-level pseudo-location information from the high-level data, which could be used in application like network management and proximity detection, where the very high accuracy location is not needed. Here's an example, outdoor localization. That's where is a GPS route, and this channel charting can be approximate this localization path pretty good. And for sensing, we can build machine learning model for enhancing very low-level sensing, removing noise and combining weak nonlinear signals, for example, pre-processing 3D terahertz imaging. Then we can enable high-level reasoning from raw data, building classification and regression models. For example, active and passive sensing for detecting and recognizing object. For example, using high frequency rates radar, where we can build this kind of 3D model to detect and recognize object better. And of course, combine different kind of signal optimally to make better accurate models for sensing these kind of raw high-level reasoning from the raw high dimensional measurements. And some other application, for instance, using passive radio sensing, we can build this kind of non-invasive recognition of human behavior and context. For example, recognizing daily activities, gestures, biomedical conditions, we can do remote sensing of environment, parameter estimation, different variables, materials, substances, and we can use these models to extract feature for localization using the supervised and unsupervised techniques as an intermediate step for more precise positioning. And then final, some general challenges and open problems for machine learning. So lack of labeled data, we can apply semi-supervised learning, transfer learning, self-supervised learning kind of ideas when we have only small number of labeled data and large number of low-cost unlabeled data. Online learning is another topic which is very open problem in machine learning in general and will be very important in 6G system when those will be more adaptive. So idea is that the static trained models can be adapted in the changes in the environment online manner using approaches from continual learning, reinforcement learning, sequential Bayesian model. So Bayesian framework provides one kind of framework to do the online updates of posterior probabilities. Then the interpretability of those models, so we want to quantify the uncertainty and out of distribution properly. And also these complex system will have a lot of distributed sensor and data locally, so we need to apply distributed and federated kind of learning to learn energy efficient models, and which will be also secured and privacy for the user point of view. Thank you, that was all.
Okay, thanks, Jaakko. Thanks for discussing the machine learning algorithms for enabling intelligent localization and sensing systems. I also would like to remind the participants to pose your questions using the Q&A dialog box. Our next presentation is discussing the interplay between sensing and communication, and will be given by Henk.
Hi, yes. So my name is Henk Wijmeers, and together with Tommy Svensson, we will give this short talk on 5G sensing and communication convergence. And we are both with Chalmers University of Technology in Gothenburg, Sweden. The first question you may ask yourself is, does 6G need localization and sensing? And for that, it's good to maybe revisit the status in 5G. So this figure here on the right shows a 5G base station sending a narrow beam to a moving vehicle, tracking that vehicle with this beam, and that may be faced with an obstacle. So based on this, you can already see that for beam alignment and beam tracking, position information can be useful, no matter where this position information comes from. It's also useful for blockage avoidance and in more general for proactive resource allocation. And there's been a lot of work in this area, and some of the papers are listed there on the right. And I would say that for sure 5G can benefit from location and map information, but maybe it's not strictly needed. In 6G, as we have seen, we will use, instead of pencil beams, we'll use ray beams, I've learned. And this will entail an enormous amount of overhead to kind of connect, unless you have location information. And when I mean location information, I don't just mean 3D position information, but also 3D orientation information, because an object has 3 degrees of freedom, and those need to be tracked in real time for exploiting it, for instance, for beam forming and beam alignment. In addition, of course, map information, channel charting, all useful to predict where obstacles are. And I would say that in contrast to 5G, 6G must harness location information. It's not a question anymore if it should, it will. And the interesting story here is, of course, that 6G itself can provide this information that is needed. And I've broken down the remaining of the part of this talk into kind of 6G as a bistatic and as a monostatic sensor. So the figure here on the right shows a 5G base station illuminating an environment or a complex multipath environment, and then the user receives a signal. And from this signal, the user can, in principle, estimate its own location, figure out where objects are in the environment, synchronize itself to the base station, figure out its orientation, and track moving and static objects. The reason it can do this, it has access to a rich variety of time and angular measurements. And to me, one of the main things that are attractive in 5G is that we turn multipath from a foe to a friend. So we can use multipath to improve our positioning. And this in turn allows mapping of the environment, is known as SLAM, and also tracking of passive objects, SLAT, even if the line of sight is blocked. Now, the properties that make this possible in 5G, which is the fact that you have higher bandwidth, higher frequencies, and more antennas, will be even more strongly pronounced in 6G. So you will have better delay and angle resolution. But there are two, I think, new topics that have emerged, which is intelligent surfaces, which can allow shaping of the environment, not just for improving communication quality, but also for positioning and mapping quality, and the use of artificial intelligence to solve those problems for which model-based approaches are not suitable. So I just go briefly a little bit deeper into those two topics. So this figure here is showing a very complex propagation environment, which is described by an enormous amount of parameters. And here AI can be used to perform dimensionality reduction. So it can provide kind of very compact ways to represent the environment, and this can be used for location-based resource allocation. The figures here on the bottom show potential use cases of intelligent surfaces for positioning. So localization under line of sight blockage, near field effects, localization of very complex environments, and also augmented reality. We've seen already some of these topics in the previous presentations. But very concretely, what to me intelligent surface provides is a number of things, right? First of all, it provides a new reference point. If we know where they are, they can serve as a kind of anchor. They're automatically synchronized, so there's no external synchronization needed. They are synchronized by nature rather than by us engineers. They provide angle of departures, so this is very useful for positioning. If they are sufficiently large, there's also wavefront curvature and near-field propagation effects that we can exploit for positioning. And I like to say that with intelligent surfaces, we turn multipath not just from foe to friend, but really to a partner who can actively help us localize. A similar story can be applied for monostatic sensing. So just to recap, in monostatic sensing, a transmitter illuminates an environment and looks at the backscattered signal to estimate properties of the environment. So it can estimate ranges, velocities, and angles. The downside of this is that you need full duplex operation because you need to listen as you transmit. But on the other hand, you have automatic synchronization because transmitter and receiver are co-located. And there's been a lot of work on using 5G and even 4G systems as radar, often using MIMO OFDM, which is really different from what people are using in radar, where they use very dedicated waveforms such as FMCW and PMCW. But no matter which waveform you use, performance is really dictated by the bandwidth that you have available, which relates to range resolution, coherent integration time for velocity resolution, and beam width for angle. Right? And especially bandwidth and beam width will be much greater in 6G. And I hope that 6G will be the first G that will provide radar sensing that is on par with commercial systems. So maybe it can provide automotive radar. And this is why I like to show this picture between two cars and ask yourself, is the question, is it 6G or is it a radar? And I think it, and I hope it will be both. Of course, those same enablers that I talked about in the bistatic case, such as intelligent surface and AI, of course, will here lead to many new opportunities. There are severe challenges with power consumption. I think it's very hard right now to sell even a 5G radar to an OEM, and also to guarantee radar performance, because we need to provide radar with a certain period, with a certain performance, especially because these are often safety critical systems. The benefit will be, of course, also that we can share information between radars. We'll create a radar network which will provide much more information. And this is now in a kind of active research area by itself with its own name, JRC, Joint Radar and Communication, which focuses a lot on spectrum sharing and waveform design, such as OTFS to replace OFDM with its high PAPR. I now give the floor to my colleague, Tommy Svensson.
Thank you, Henk. So location-aided communication, well, the idea is not new. Back in 4G times, GPS or mobile-assisted GPS was used for handover and advanced coordination. With 5G, we saw the opportunity to enhance localization and also to use location information for more fine-grained needs in mobile communication network, like side link coordination or device-to-device underlay network coordination and routing, and opportunity for proactive resource allocation. As Henk also highlighted before, The new thing with 5G is the new radio based on millimeter wave. And there we have the big challenge on beam finding, beam alignment, and beam tracking. So typically we have been using network assisted on sub-6 low carrier frequencies. But when we don't have that, if you're standalone, we really benefit from location information. And this will be even more prominent in 6G. We will go on higher carrier frequencies, denser networks. So to track also reflectors and blockers will be really beneficial, and to also enable cooperation between the users for mapping and enable proactive allocation with situational awareness. Next. So what about sensing in 6G, in particular terahertz? Well, in general, how should we do this, and what do we mean with sensing in 6G? We can mean sensing deeply integrated into 6G wireless communication networks, that this uses the same infrastructure, tailor-made signals, part of the 6G area interface design, sensing, reusing the communication signals, etc. And then mobile network operators might be the provider of the sensing service. Or we do it a little bit less integrated, for some cases, sensing enabled by 6G connectivity, but where the sensing part is not co-designed with 6G area interface. A good example is established a radar system that start to cooperate with the help of 6G connectivity. So cooperative sensing that inherently needs 6G connectivity capabilities between the cooperative sensors, or sensing whose data is MLA processed in the cloud, in particular when the latency, high capacity, very reliable wireless connectivity is needed to the cloud, such as tight control over communications and computing in such a distributed cloud when that's required for sensing system. Or in the bigger broad scale, non-connected sensing, that is, or sensing not connected via 6G at least, that still benefits from hardware and software development in the 6G ecosystem. A reminder that the mobile communication ecosystem is huge, and it really benefiting R&D and efficient manufacturing and testing capabilities from the 6G industry. 6G could then drive availability of low cost and high performance terahertz hardware, enabling sensing in so far not economically viable domains. And we illustrate this with a flagship initiative we did 2018 in Europe called TeraFlag, where there were 176 organizations signing the initiative. Next. So we think there's a huge potential to converge into a combined 6G system in some kind of combined sense. New enablers, we have talked about, application opportunities, there are many. There are also a lot of challenges that we highlight so far today, and maybe more in the next speech. So if you're interested, please read further in our 6G white paper on localization and sensing.
Thank you.
Okay, thanks for highlighting the importance of such convergent communication, localization, and sensing systems. Along the same lines, next we have the presentation from Andre talking about radar and communications.
So we're going to talk about active radar sensing using joint communication and RF sensing. And that's basically a follow-up of what Henk has mentioned when he talked about monostatic approach of radar. I work at the Barkhausen Institute, which is a young research institute in Dresden, Germany. So what we are talking here is quite an obvious idea, because both radar and communications, they use the same physical phenomenon of the propagation of electromagnetic waves. So why not do both of them together, right? That's not how it's been done so far, but we believe that in 6G, that's the way to go. That radar sensing will be an integral part of 6G and not something separate as now. And what do we gain from it? We think that the main reason to do this is to share the spectrum, right? We have a huge opportunity for spectrum sharing here. We will need more spectrum for 6G, definitely. And radar spectrum nowadays is very underutilized in most places. For instance, we have a very high usage of radar spectrum on the roads or on the streets, mostly for automotive applications. But when we are at home, when we are in the office, the whole radar spectrum remains currently unused. Just to give some basic numbers, currently we have 5 gigahertz of spectrum allocated just for radar applications, mostly for the automotive scenario, whereas the whole 5G Spectrum is about 2.5 gigahertz, even including the millimeter wave spectrum. At the same time, we have basically just 1% of the population which drive cars with radars, whereas 91% of the population use smartphones or feature phones. So we have much more spectrum for an application that's used by a very tiny proportion of the population. That's just to give some numbers here. I mean, it's hard to talk about spectral efficiency from radars, but just some numbers. Let's say if we have a 50 millisecond radar cycle, that we get radar information every 50 milliseconds. And if you think that this information contains maybe 10 bits of information, we have a very, very low spectral efficiency. That's just to show that we still have a long way to go, very high potential to improve the occupation of this radar spectrum. And what do we gain from it, apart from spectrum sharing? Once we have this functionality that we have both radar and communications using the same spectrum, using the same hardware, both the communication and radar will we have some new functionalities that will be enabled. For instance, interference among radars is now already a problem. There are maybe too many cars using radars in some places. And we can use, for instance, this communications channel just to coordinate the radar transmission and reduce interference. We can also use the communication channel, for instance, to perform sensor fusion, to combine the information from many different radars in just one centralized place and improve the information that we get from the radar. For instance, we can have an improved radar imaging, or in the future even in terahertz. But also the radar can improve the communication side. For instance, if we can detect some obstacles in the communication path, we can choose the beams more efficiently, so we can improve beam management using the radar information. And once we have this functionality, of course, many other possibilities will come. So why don't we have it yet? So why are we talking about this just now? And there are some new enablers that will help us reach this vision. For instance, as Henk has mentioned, we are moving up to new frequency bands with very high bandwidth, and that's something that's needed for radar. So that's something that's coming up in 5G and probably in 6G. We have the mobile edge cloud with lots of computational capabilities, very close to the wireless connection. And this mobile edge cloud will probably be equipped with machine learning. That machine learning will be an integral part of 6G systems that will be very useful for radar applications, radar detection. And of course, we are likely to have ever more antennas and finer beams, which are also very helpful for radar and for localization applications. So we believe then that in the future, we will have radar just as an additional service for the wireless network. So as we have right now in 5G, we have different types of communications like broadband connectivity, URLLC, or machine type communications. We believe that in the future, we will have just a menu of different applications, and radar sensing and localization will be just another application for the wireless network. And once we have this, we can think of many different application scenarios. Nowadays, maybe the scenario which most extensively uses a radar is the automotive scenario, where they are already extensively used for many functions like adaptive cruise control, lane change assistance, cross traffic alert. As I mentioned before, the interference among these radars is already increasing. It's already a problem. But again, once we have this feature, we can think of applications in drones and robots, for gesture recognition, for health monitoring, like heartbeat monitoring. And once we move up to higher frequencies like terahertz, we can even think of spectroscopy applications like detecting gases or the chemical composition of food and things like that. So many others applications for sure will come once we have this combination of communications and sensing in the same place. There are different approaches for the problem in the literature. What we have seen in the past is attempts to have coexistence between radar and communications using the same spectrum, which is a sort of a cognitive radio approach. We have also what's called RedCom, where we have a radar system with some embedded communications capabilities, but usually at a very, very low data rates. We also have the passive radar approach, which we can call maybe Comrade, where we use existing communication system waveforms and passively detect the objects using the signal reflections. But what we think that will be the way to go in the future is called joint communication and radar, where we have one single waveform that can be exploited for both communication and radar, and then can be adaptively allocated to either one of these purposes. As we have seen before, there are some situations in which we need lots of radar. There are situations in which we need more communications. So we should be able to adapt. And at the Barkhouse Institute, we are currently investigating some chirp-based waveforms. We still believe that chirps may be a good solution for this. Why? I mean, it is known that they have good ambiguity properties for radar. You know, other waveforms also have good properties, but chirps are well known. I mean, the algorithms are well known. And what's maybe more important for radar, that we can design very low complexity radar transmitters and receivers. And that may still be needed for many different applications. And we have shown that we can also easily modulate and detect the chirps also for communications. And that's our vision, but there are of course many research challenges before we achieve our goals. First of all, I have already mentioned the thing about how difficult it is to measure the spectral efficiency of a radar. And once we have one single system which supports both applications, we must have some metrics that we can compare and that we can use to decide on how to allocate the resources. So I mean, still have to know, we have to define some comparable metrics for both and some theoretical limits for the combination of communication and radar. We also have to find a waveform that's suitable for both applications. For instance, we have talked about chirp-based waveforms, but of course, FDM is also still a candidate for this kind of application. And also a question is that as we move towards the higher bandwidth, maybe we don't need such a high spectral efficiency. So maybe we can move towards the power limited regime where we can use FSK or PPM or other different kinds of modulation which are more power efficient. Managing interference will of course be a challenge. As the usage increases, also the interface will increase. So we have to allocate the resources more efficiently. We will need a joint communication and sensing MAC layer. Cannot again forget about cost and power efficiency, especially as we move to very high bandwidth. We tend to consume more energy. It would be very nice if we could avoid full duplexing, which is feasible, but it's likely to be very expensive. And for the research, we also need a unified and consistent channel model for both applications. And just to conclude my talk, I'd like to invite you all to the first IEEE Symposium Joint Communication and Sensing, which we are organizing. It will be a virtual event, will take place in February, and we have now an open call for papers with the initial deadline in the 14th of December. So please, if you're interested, please have a look at the website.
Okay, thanks a lot, Andre. I think now we can start the Q&A section. We received quite a few questions. We try to iterate among them. We will try more or less to follow the presentation order. So the first one is going to be to Hadi, and it says, how much size is the intelligent reflective surfaces require for effective area control? Could you please exemplify with a typical use case?
Okay. Yeah, so I will just share a few slides while answering. Actually, there have been a couple of questions raised on Terahertz communications, so I will try just to address them briefly in general. So the first, there was a question on what kind of enhancement to communication can reflecting surfaces provide? Well, actually, this depends a lot on what kind of use case are we after in Terahertz communication. This also, the kind of use case also affects the coverage and how we define coverage, actually. So it depends on whether we are using the surface to establish just more multipath links to enhance coverage, or to enhance coverage behind where there is no line of sight, for example, or to assist like multi-user communication. But in general, so in one use case, if we have if we just like extending a link of coverage, it's expected that for example, the power gain can increase as a factor of n squared, which is the number of antenna elements. But exact figures on merits are really depend on a lot of variables, including the frequency of operation, including how dense the elements can be fitted. So it depends on what kind of coverage. Is it like a continuous coverage or coverage in specific beams? If we're going for a discrete surface, then we're only limited to illuminating only specific directions for coverage. If we're going for more of a continuous aperture, then maybe we could have more of like holographic behavior, and then we can achieve spatial resolution in any direction. Also, it depends on what kind of metric do we decide on the coverage. So what is out of coverage, what is in coverage? Is it an outer probability or what? So actually, it depends a lot on the frequency and the use case of the surface. But there has been also questions on the power efficiency and whether it is feasible to realize such surfaces for 6G. Well, actually, the vision so far from all kind of approaches or initiatives for implementing surfaces have been that we are like looking into a low cost of fabrication as well. So this is one thing, but the true reduction in cost comes from reduction in power consumption. So first of all, just enabling surfaces that are not active, just reflect signals and can increase the power transmission. This is one thing that can substitute an active base station with that. This is a true power consumption. Also using surfaces close to base station and from a signal source can enhance the signal and transmit it to further location. This also reduces power. The fact that it is compact in size and can be like easily integrated into other technologies, especially at higher frequencies, this reduces kind of cost. But still, like there is a long way to understand its exact cost, especially if you want to implement it indoors. For example, you need to have agreements of residents and etc. So there are a lot of variables that are not yet understood. As for the cost of surfaces going for terahertz communication and whether it is really feasible, yes, at this stage, the true contributions to terahertz system are still at the device level. So we're not very sure exactly what technology will make it to be commercial and widely used. So maybe Barend will have a little bit more on the exact technologies of surfaces. But the idea here is that compared to massive MIMO system, regular systems, and compared to relays, which are not mature at all for terahertz system, how can we control a large number of transmitting antennas coherently, very densely close to each other? It might be convenient if, given also the advancement in meta surfaces, if we could, perhaps the use of surfaces for terahertz communication will be even before the use of massive MIMO and relay systems. So I think there was also a question on the kind of beamforming, what kind of beamforming solutions do we use for communication using reflecting surfaces? Actually, it's a joint optimization problem of the beamforming that's happening at the base station and the phase shifts that can be introduced by each reflecting element. And this also depends on the mode of operation of each reflecting element. Is it just like turn it on and off, or is it introducing a continuous phase that we can choose a continuous phase for each reflecting element, or is it a discrete phase? I would advise who asked this question to look, for example, there's a nice paper that summarizes these optimization problems referenced to here. Gives a nice summary of all of most of the optimization problems happening for reflecting surfaces. We also look into some even much reduced complexity beamforming solution. For example, if you could just make each reflecting element either reflect or not reflect, and just we can tune the separation between antenna elements. So this is even a reduced complexity, and the only parameter to tune is the delta, which is separation to reflecting elements. Again, there is a lot of initiatives there and a lot of works in the literature so far, a lot of optimization problems, maybe just maximize the minimum signal to interface noise ratio. Some gradient ascent solutions have been proposed there as well. Yeah, so I think these in brief were the questions on my presentation on surfaces. I would like to suggest to check the previous webinar on scoring the terabit per second goal for broadband connectivity, where there's been a more detailed discussion on the communication aspect of surfaces, whereas in this presentation we have highlighted more the prospects of combining sensing with localization using the intelligent surfaces.
Okay, thanks, Hadi. The next question is for Yang Miao. And the participant asked, what's the current state of the art of RF hardware, 5G or beyond?
I think I understood. I have answered by texting already. So,
can you give just a brief summary of your answer?
So for the hardware, I'm not sure, but there were some works from MIT and other groups are using Wi-Fi for sensing purpose. But for joint communication and sensing with mobile communication radio system cooperated by physical layer and other layers, I haven't seen such published investigations yet. But for example, if only using static MAMO systems for sensing human postures, there were works from Japan as well. And also we are working on the millimeter wave beam space for sensing human postures, but there is no published work yet.
Okay, thanks.
Yeah.
The next question is for Henk. And the participant says, do you see sensing, radar, and localization as three different areas in 6G?
I think it was nicely summarized by Andre that there will be just new surfaces on top of the existing surfaces in 5G that we already have. I don't see them as different areas, no. In all cases, you emit a waveform and then you exploit the geometric information of this waveform for different purposes, either to localize, to sense, or detect objects in the environment. So, no, for me, it's one big area with different applications.
Okay, thanks. The next question is for André Barreto. Won't chirp-based waveform have a hit on achievable communication capacity?
Yes, I mean, we have seen that we can actually transmit chirps at very high spectral efficiency, and there might be some challenges regarding equalization, because that's like basically the great advantage of OFDM to make equalization easier. But it is doable. But apart from that, we can even think that maybe we don't need such a high spectral efficiency since we are talking about very high bandwidth. Again, maybe we can talk about communication schemes which have a lower spectral efficiency, but would still achieve a pretty decent data rate. So, but that's an open question. That's still an open research topic.
Okay, thanks, Andre. I think we are kind of running out of time, so the questions will be published online so that everybody can follow afterwards. Before ending this session, we just would like to make a few remarks. So like, please continue, keep the discussion like going. So like try to, when you refer to our 6G white papers and webinars, try to use this hashtag like marks. Another thing that we would like to bring to your attention is that the next webinars, we need to change slightly the date. So the next webinar that will address a deep dive into the 6G white paper on validation and trials for vertical towards 2030 will be on 2nd of December. And the following, that's on regarding 6G research visions, webinar series 6G networking will be on December 9. So I think from our side, it's all. Thanks a lot for joining us. and hope to see you in the next webinar session. Bye. Bye, all.